get the feeling there's a hidden code to the universe? You know, a single pattern that could possibly connect the way rabbits breed, the way a galaxy spirals, and even the proportions of a masterpiece painting? It sounds a little out there, I know, but the whole story kicks off with a simple little puzzle from over 800 years ago. So let's dive in and see how deep this rabbit hole goes. And really, this is the big question we're tackling. We're going to follow two totally separate threads, one from 13th century Italy and another all the way from ancient Greece. And we're going to watch as they just weave together in the most surprising and honestly beautiful ways. Okay, so here's the classic problem. I want you to picture this. You take one pair of newborn rabbits, one male, one female, and you put them in a big walled-in area. Now, the rules are pretty simple. Rabbits can start having babies after their second month of life, and once they start, each fertile pair has one new pair every single month. So the question is, how many pairs of rabbits are you going to have after a full year? To get our heads around the answer, we've got to go back and meet the guy who came up with the question in the first place. This is Leonardo of Pisa, though you've probably heard of him by his nickname, Fibonacci. He was this brilliant Italian mathematician, and back in 1202, he published a book called Liber Abaci, or The Book of Calculation, and inside was this little rabbit puzzle. But you know, his book did something way, way more important. It helped bring the Hindu Arabic numeral system, the numbers 0 through 9 that we use for literally everything today, to Europe. A total game changer. So how does this whole rabbit population actually grow? Let's just walk through it. Okay, month 1, we start with our single pair. After that first month, they're still too young, so still just one pair. But at the end of month 2, boom, they have their first litter. Now we've got 2 pairs. A month later, that original pair does it again. They have another set of babies, but that second pair isn't old enough yet. So now we're up to 3 pairs. And the month after that, well, the original pair and their first kids are both ready to go, so they each produce a new pair. And just like that, we jump from 3 pairs to 5. And right there, you can see the pattern starting to pop. You get this sequence, 1, 1, 2, 3, 5, 8, 13, and it just keeps going. This is the famous Fibonacci sequence. And what makes it so cool is that it's recursive. Think of it like this. To get the next number, all you do is add the 2 numbers that came right before it. So 3 plus 5 gets you 8, 5 plus 8 gets you 13. It's this super simple, elegant way of growing. Now let's put a pin in that for a second because our next clue is going to take us way back in time to ancient Greece. So centuries before Fibonacci was even thinking about rabbits, mathematicians in a whole other part of the world were obsessing over a different kind of pattern, one they found hiding in shapes. You see, the ancient Pythagoreans were just fascinated by the pentagram, the 5-pointed star. And as they were studying it, looking at the relationships between the links of all the different lines, they stumbled onto something amazing, a constant ratio that just kept showing up over and over again. It seemed like it was a fundamental part of the shape's DNA. What they had found is what we now call the golden ratio. We use the Greek letter phi to represent it, and it's this really weird number. It's irrational, which just means the decimal points go on forever and ever without repeating. For our purposes, it's roughly 1.618. Now, you have to understand, this discovery totally freaked out the Pythagoreans. I mean, their whole worldview was built on the idea that the universe was neat and tidy, governed by whole numbers and simple fractions. So finding a number that you couldn't write down as a clean fraction, well, it was just deeply unsettling. It flew in the face of all the logic they thought they knew. This divine proportion, as some called it, also gives us this really special shape, the golden rectangle. Its sides are in that perfect ratio. And here's the wild part. If you chop a perfect square off of one end, the little rectangle that's left over is another, smaller, perfect golden rectangle. You can just keep doing this forever, and you'll always end up with the same harmonious proportions. It's incredible. Okay, so we've got a number sequence from breeding rabbits and a ratio from ancient Greek geometry. I mean, on the surface, they have absolutely nothing to do with each other. But what do you think happens when we smash them together? All right, let's go back to Fibonacci's numbers for a second. Let's try something. What if we take any number in the sequence and divide it by the one that came right before it? So 3 divided by 2 is 1.5, okay. 5 divided by 3 is about 1.66. 8 divided by 5 is 1.6. Huh. Now watch what happens as we go further down the line. 144 divided by 89. The answer gets closer and closer to a very, very specific number. And there it is. The ratio between those Fibonacci numbers gets closer and closer until it basically becomes the golden ratio phi. It's unbelievable. These two ideas, born centuries and cultures apart, one from biology, the other from pure geometry, are actually two sides of the very same coin. And we can even see this connection. It's beautiful. If you draw out a series of squares with side lengths that match the Fibonacci numbers, so a 1 by 1 square, another 1 by 1, then a 2 by 2, a 3 by 3, 5 by 5, you get the idea, and then you draw a smooth curve connecting the corners, you get this perfect spiral. It's a spiral whose growth is dictated by phi. Now, this isn't just some neat mathematical party trick. It turns out this pattern, this code, is written absolutely everywhere in the natural world. I mean, just look closely at a sunflower sometime. You'll see the seeds are arranged in these two sets of interlocking spirals, right? One set goes clockwise, the other goes counterclockwise. Well, if you actually count the number of spirals in each direction, you'll almost always find two back-to-back Fibonacci numbers. And that same spiral shape, it's right there in the chambers of a nautilus shell, each new chamber growing at a rate that perfectly mirrors the golden ratio. And get this, it even shows up in us. The bones in your finger, from the tip down to your knuckle, their proportions are a pretty close match to the golden ratio. It's what Leonardo da Vinci was exploring in his anatomical studies, how these ideal proportions pop up all over the human body. So if this ratio is so fundamental in nature, it kind of makes sense that we humans, whether we know it or not, have been using it in the things we create. It's like a blueprint for what we find harmonious and beautiful. And people have found this divine proportion everywhere. We're talking about the design of ancient wonders like the pyramids of Giza, in masterpieces like Da Vinci's Mona Lisa. It even shows up in modern architecture like the CN Tower in Toronto. And get this, some people even argue it's in music, that composers like Beethoven actually use the golden ratio to structure his symphonies. Which leaves us with one last, massive question. Is this mathematical code a real, fundamental law of the universe that governs how things grow and what we find beautiful? Or are our brains just so good at finding patterns that we see this one everywhere we look? Is it a blueprint that's actually written into reality, or is it more of a reflection of how our own minds work? The answer is probably a little bit of both. What do you think?